Let's continue with the second part.
Thank you. So whatever I'm going to speak about, it is joined with Balázs Bárány, Boris Solomyak, and Adam Śpiewak, who is from Warsaw. Now, I mean, usually Warsaw. So our setting that in the symbolic space, we all until now I spoke about it was that we had an iterated function system which depended on a parameter, but now we are going to consider also a family of measures, and we take the push forward of the family of measures, and I showed I decided to divide the talk in a way that today I would rather talk about this theorem, maybe a couple of words about the proof, and then I will show you applications next time. So here are listed these famous A1 to A4 assumptions, and I will go through them later. So yet again, we are given on a compact interval. We are given a one-parameter family of C1 plus theta iterated function systems, and then they depend smoothly on x and lambda. And what it means that there exists such a delta from the interval 0, 1, such that all the mappings are not only 1 plus eta, but 2 plus delta smooths, and the dependence on lambda is 1 plus delta smooths uniformly, and the second partial derivatives are Hölder uniformly both in lambda and x. And this is our always reoccurring assumption, which is over there, that all the derivatives are separated from 0 and 1. So here is 0 and here is 1. So these are the assumptions. But I would like to tell them with more detail, just to remind you. So what is A1 actually? So A1 says the following, that if you take M1, which is the supremum for all possible parameter value, and this A is just the alphabet. So A is 1 to M. This is A. And so you take the supremum of the second derivatives with respect to x, and the supremum one, then this is finite. And there exists C1, C2, such that you see this is this Hölder continuous assumption about the second derivatives. Here we fix lambda, and then we take the second derivatives at x and y, and we have this inequality. And if we fix x, as you see over here, we fix x, and we change lambda, and still we take the second derivative with respect to x, then we have such an inequality. This was A1. This was stated as f lambda I are C 2 plus delta smooths on x uniform. And then A2 is this assumption that the mapping from F to Fj lambda is C 1 plus epsilon smooths So there is a constant such that if you take the derivative with respect to lambda at lambda 1 and lambda 2 for a fixed x, then you have this inequality. And then finally, there is only one more boring assumption, which is that this M2, which is the supremum for all possible things. So what was M1? M1 supremum for lambda and supremum for all indices, and this is exactly the same. And here it was that the second derivative with respect to x, and now the second, this mixed derivative are finite, and these inequalities hold. So about the mixed second derivatives, we have that this is smaller than x minus 5 raised to the power delta, and then similarly, just here x and y were different. In the next line, x is the same at these two places, but here lambda 1 and lambda 2 appears, and here it was smaller than this, and now this is smaller than this difference. So you see that the dependence on lambda and x are very much smooth. This is what we assume. One more time, I like to recall that this is the alpha energy. If you have a metric, so this is a metric space, and this is the alpha energy, and we will consider several times the correlation dimension. The correlation dimension has various definitions, but this is the definition which is suitable for us. So the correlation dimension is the supremum of alphas for which this energy integral is finite, and then the correlation dimension is smaller than equal to the Hausdorff dimension of the measure, and this inequality is quite simple and very, very useful. Because in many cases, when we want to compute the dimension of the measure, then we give this estimate from below, and you can see what was the Hausdorff dimension of the measure. The Hausdorff dimension of the measure. What was the Hausdorff dimension of the measure? You take all the sets of full measure, and you consider the one with smallest dimension, and almost you take infimum, doesn't matter. So you can think of, very roughly speaking, the Hausdorff dimension of the measure is the smallest dimension of a set of full measure, and that is bigger than this, because if the set has full measure, then if you restrict your measure mu to that particular set of full measure, then for this restriction, this energy integral will be the same. And if we go back to what we discussed earlier, what we discussed here to the potential theoretic characterization of the Hausdorff dimension, it is exactly that. So it follows from the potential theoretic characterization of the Hausdorff dimension that the correlation dimension is a lower bound on the Hausdorff dimension of the measure. That's very, very important, because the Hausdorff dimension of the measure has this it has various forms. You can express it as the essential so the essential supremum of the limit. So there are various expressions, but not as nice as this expression, what you see over here. Here, this is expressed basically in terms of integrals, what we very much like. That's why it's very handy to work with the correlation dimension. Okay, and yet again I repeat that this is the metric d lambda, which is the length of the corresponding cylinder. This is the metric that we use. And then if you use this metric, then this is a good metric, because if you apply this metric on the symbolic space, then the Hausdorff dimension of the measure mu lambda with respect to this metric, so this mu lambda is a measure on the symbolic space, and this Hausdorff dimension is the entropy divided by Lyapunov exponent, so it is a good metric. Now we will need to introduce a couple of definitions. I'm sorry, these are not very much uplifting, but we need to do that. So Sobolev energy, the Sobolev energy is you take a measure and you consider its Fourier transform, and you form this integral, and this is the Sobolev energy. And the Sobolev dimension is the supremum of those alphas for which this Sobolev energy is finite. Now the Sobolev dimension is very useful for us because if the Sobolev dimension is bigger than 1, then the measure is absolute continuous with L2 density. So it's a very important property. So one more time, the Sobolev dimension, which is expressed in this way, if you can prove that this is the Sobolev energy, the Sobolev dimension is here, and if you can prove that this is bigger than 1, then the measure is absolute continuous. If you can prove that the Sobolev dimension is bigger than 2, then the density is continuous, so eventually the fractal on which it lives contains an interval. So that's a very, very useful dimension, the Sobolev dimension. Now, this Sobolev, this I alpha, which is the Sobolev energy, it is this with the usual T energy. This is the usual T energy. And these two people are almost the same if alpha is in between 0 and 1. But otherwise they are different. So for 0 and 1 they are just almost the same. So the correlation dimension is the same as the Sobolev dimension if the Sobolev dimension is in between 0 and 1 from this. So one more time, although this I alpha nu has a somewhat different form from this expression, which is the alpha energy, this Sobolev energy and the usual energy, they are the same if the Sobolev dimension is in between 0 and 1. Okay, so these are just a couple of definitions. And so for a Borel measure, we have the Sobolev norm, which is this not very inviting expression. And then I told you what is the Sobolev energy. You see over here, this was the expression. But people, instead of this absolute value of psi, you can write 1 plus absolute value. It will be the same. I mean, the value will not be the same, but if you write 1 plus behind this here, then you see this one. If you compare that one with this, then they are finite exactly the same time. And all of these things, if you want to read about that, you can find this stuff in Mattila's book. Good. As a second book, because Mattila, wrote 2 books, 2 very, very good books. The first one is 1999, and this is about general geometric measure theory, and that's really a fantastic book. And this second book, what I'm referring to now, this is mostly about this fractals and Fourier analysis. So if you need to work, you are working on fractal geometry and you need to know something then I would very much recommend. That's a great book. There are a number of typos, however. I myself found at least 10 typos, which I showed Matilda and we discussed it, but unfortunately I lost the list. So it's not very helpful. But I can tell you that most probably there should be some list of erratas somewhere. So now we have arrived. I mentioned you 4 criteria, which were A1, A2, and A4, and they just postulated that everything depends on everything very smoothly. Now here are further assumptions about the measure, and I would like to somehow make a note about these assumptions, because later we will need to refer to them. So it's good to keep in mind. I will be not as precise as here I was. So M0, what is M0 assumption? It says that if you have lambda and tau, which are close to each other, and then you would like to see the measure that because we are talking about a one-parameter family of measures, so you consider the measure which corresponds to parameter tau, and the measure, you measure a certain cylinder, and you compare this measure to the measure of the same cylinder for this measure lambda, then the ratio is smaller than or equal to e to the power epsilon multiplied by the length of this finite world. And then I would also like to write MC means simply continuous. It simply means that the entropy depends continuously on lambda, and the Lyapunov equivalence continuously on lambda. It's easy to remember. So what is this? I would not like to write down all of those things. Simply M is that if you take the measure which corresponds to a certain lambda and compare it which corresponds to a lambda prime, so the measure of a cylinder, and then correspond, compare it to the measure of the same cylinder, then this is smaller than equal to e to the power constant times, well, you can think of theta is equal to 1, as Mark also spoke about C2. If we are in the C2 case, then theta is equal to 1, so it's, then the formula is easier. So E C times lambda minus lambda prime on theta and the length of I. This is the other condition, and all of this lambda and theta, they are whatever they need to be. And then the last condition is just the old transversality condition we have already discussed, so T is just the transversality. So these are the conditions, but I'm afraid there will be some more conditions later. So I just like to give you some examples. If mu lambda is a Gibbs measure, you remember what was Gibbs measure? Gibbs measure corresponding to this potential phi lambda. In the previous lecture, we spoke about Gibbs measure. I would like to recall the Gibbs measure, the definition of Gibbs measure. If I find it's here. This was the definition of Gibbs measure. You see that. So if mu lambda is a one-parameter family of measures on the symbolic space, such that this is a measure which corresponds to this one-parameter family of potentials, and then if you know that the dependence of this phi lambda on lambda, you know only that this dependence is continuous, then you have M0. But if you know that this dependence is even Hölder, then you know that this condition holds. The condition M holds. And now there will be a number of theorems which I would like to state. And the first theorem is this. It says that if you have a condition A1 to A4, which means that everybody is very smooth, and this assumption holds. And additionally, you have transversality condition, and additionally, you have M0 condition. Then the Hausdorff dimension, then for Lebesgue almost or parameter, if you project down this one parameter family of mappings with the corresponding projection, then the dimension is what it has to be, so the minimum of 1 and entropy of a Lyapunov exponent. So the dimension doesn't drop, because under the projection the dimension never increases, but it does not drop, at least if these conditions hold. Okay. Now I go back, so I just wanted to recall the definition of. Okay. Yes. Now the second theorem. Yet again, we assume that A1 to A4, so everything is very smooth, and the transversality condition hold, and mu lambda is a parameterized ergodic invariant measure satisfying M. So now we assume this condition M. Then for Lebesgue, almost all parameters, we have that this condition holds. Well, what is this? That the Soboyev dimension of the push-forward measure is bigger than equal to the correlation dimension. This is on the symbolic space. So the minimum of this and 1 plus minimum delta rho, and these people come from these conditions. Here rho comes from here, and the delta was included in these conditions A to 4. So this is not very much interesting for most of you, but as a result of that, what we get it is that so this implies that the projected measure is absolute continuous if this entropy of a Lyapunov exponent is bigger than 1. So to state the third theorem, if phi lambda is a potential such that the dependence, sorry, this is not omega, but this is I, and this is uniformly Hölder, then these are properties P1 and P2. So if you have these smooth assumptions, the transversality conditions, and these Hölder conditions, then if you push forward mu lambda, which is the Gibbs measure corresponding to phi lambda, then you do not lose dimension, and if this entropy of a Lyapunov exponent is bigger than 1, then the projected measure is absolute continuous. And then there is finally a last theorem, which is the most frightening looking, but these are just further smoothness assumptions. So if you are given, so mu lambda is a family of Gibbs measures corresponding to continuous potentials. And for a continuous potential, the k variation of the potential is computed in the following way, that you take two elements from the symbolic space, and their common prefix has length k, then you can take the supremum for such omega 1, omega 2's the supremum of this difference, and this is the k variation, and the assumption is that the maximum for lambda of these k variations are uniformly smaller than this b times alpha to the power k, so some kind of uniformly Hölder assumption, and a similar uniformly Hölder assumption is stated over here. So if you have two parameters lambda and lambda prime, then this difference, then this inequality holds. And in this situation also, in this situation condition M holds, and if you push forward the measure, then it will be absolute continuous if the ratio of Lyapunov over entropy over Lyapunov exponent is bigger than 1. So these are basically our theorems, and they are not beautiful, but I will tell you that it will be much more interesting when we come to the applications. So these theorems, basically all of them say that if you have a certain kind of smoothness on all kind of parameters, because here there is a family of measures and a family of iterated function systems, and these iterated function systems gives you this push forward, these natural projections. So if everything is smooth enough, then typically for almost all parameter, neither the dimension drops nor, well the dimension doesn't drop, and if the entropy of Lyapunov exponent is bigger than 1, then the projected measure is absolute continuous with L2 density. So these are basically, we wanted to express this, and we needed very, very technical assumptions. And of course, these theorems have rather technical proofs. Maybe I would talk a little bit about the first theorem, the proof of the first theorem, because it is about only the dimension, and that's less frightening than that. What I need to tell you it is that in a less general setup, the first theorem was already in a more specific content had already been proved by Bárány and Mihály Rams. So our main contribution is about the second, about the theorem related to absolute continuity, but it is too complicated, I guess, to talk about the proof right now. So I would more focus on the first, on the proof of the first theorem. So this is what we would like to prove, that the correlation dimension of the push forward measure, so this is a measure on the line, and this is a measure, this mu lambda d lambda, this is on the symbolic space, and we would like to prove that when we go from the symbolic space to the line, then we do not lose correlation dimension, at least typically. This is what we would like to do. First, because here everything depends on the so here the measures depends on the parameter. Probably it's good if I give you the proof first for the case when the measure actually does not depend on the parameter. Then the proof is much easier. And maybe I would tell this situation for the first, and we will see what happens after. So what we would like to do it is that we would like to prove this inequality if there is no dependence of lambda, no dependence on lambda of the measure. And we would like to prove that this holds almost surely. So we take this integral of the energy, and the energy itself is defined here, what I show you. So this is the energy, and we take its integral, and then we write down this difference in this way. So this is exactly that, and then we pull out this f alpha just from, this is not exactly equal to, but here we use Lagrange theorem, and we should write the derivative of this map. But the derivative of this map at any point is basically the length of the appropriate cylinder. So we get this line. And then here is something which I don't want to detail very much, that here we make two steps. One of them is that we change from parameter lambda to parameter lambda 0, and for that we need to pay a price that here an epsilon appears, and then when we change the order of integration, then this integral with respect to this, it will give us a constant. That is the point where the transversality is used. So and then basically we get the result. So this is the proof, not exactly, but roughly speaking, when we do not depend on the parameter. And then if we really depend on the parameter, then I just like to give some. The first goal is to prove that the correlation dimension of this projected measure is at least the correlation dimension on the symbolic space for almost all lambda. So the classical transversality argument gives this inequality holds for a fixed lambda 0 when lambda is just from neighborhood of lambda 0, and then we claim that the dependent, this function what I show you is continuous, and this function is also continuous. And if we knew that it is the case, if we knew that it was true, then what we can say it is that, one more time, this is what we want to prove. So we start from here, and we change lambda to lambda 0, because we know that somebody is continuous. This person is continuous. So if lambda is close to lambda 0, then for the price of negative epsilon, we can change this lambda to lambda 0. And then using the transversality, this person is bigger than mu lambda 0 d lambda minus epsilon, and yet again from continuity, yet again losing from this lambda 0 to lambda another epsilon. So altogether we get the proof if we know that these mappings are continuous. And so these two mappings are continuous, and the continuity of these mappings can be described basically as it is written over here. I am not sure that I would like to get into this computation, because it's not really uplifting. Perhaps I will just skip it, because it's difficult to follow. But the idea, at least, of this proof about that we do not lose dimension is not very complicated. So I would just skip it. If we here I wanted to explain that the same idea doesn't work. The same idea would not work if we want to do about the positivity of the absolute continuity of the measure, then the same idea could not be used. I would just skip that. And these are the definitions that I have already mentioned. We have already spoken about. These are the tools that we need for the absolute continuity. We have considered it. And here there is no continuous property. So as I mentioned, in the case of the dimensional estimate, we had this continuity property, and when you consider the Sobolev dimension, then we do not have continuity property. It is it is quite you can find quite easy counterexample which is written here, that we do not have continuity for the Sobolev dimension, and that's why we need to develop a certain method which was introduced by Perez and Schlager. We need to change that method. For that method, functions play very important role, which are called Littlewold-Paley functions, and these are functions of Schwarz class. You know what is functions of Schwarz class? Okay, Schwarz class means that they tend to zero faster than any x to the power negative k, and not only the function but all derivatives of the function as to zero, as you go to infinity faster than x to the power negative k. So this is on Schwarz class, and somehow satisfies this. The support of the Fourier transform is in this annulus, and the sum, as this sum is equal to 1, and this is somehow a standard trick in harmonic analysis, that the Sobolev dimension can be estimated with such an integral with these Paley-Littlewood functions. And then the difficulty is that this psi changes sign, so it's not easy to handle it in our case. And here is a certain idea how we handle it, but I'm afraid that it would be a little bit boring to get into exactly the details. But the bottom line is that we need to handle these kind of difficulties, and it requires a lot of calculation. Sorry, I know that this is kind of boring, but I wanted to say something about the proof. And I am not going to say more about the proof. So this was what I wanted to say about the proof. I have how many minutes? 10 more minutes?
10, 11.
Okay, so I would finish. If you have any question related to that, then if I can answer, then. So the proofs are very complicated and rather boring. But let me just state the theorem one more time. Because the theorem is easy to understand, and when now we will get to the applications, then we don't need to remember all of these things, what we discussed. So the theorem one more time is that if you have the usual transversality situation, then you have a one-parameter family of iterated function systems. And in the symbolic space, you have one single measure, and you push forward the single measure with this family of iterators for different parameters with different projections. And it happens very frequently. For example, when you consider this kind of what we discussed several times, this kind of Gibbs measure. So if we go back to the beginning there was this definition, one particular Gibbs measure, that potential, maybe I am not going to find it, but the potential, which is the most important one, when you have this phi lambda, what is that? You take at I, what you do it is that you take I1 lambda and you differentiate it, and you need the logarithm, and you differentiate it at phi lambda sigma I. And this is the potential, which is the most important potential. So that Gibbs measure, which is the most important Gibbs measure, corresponds to this potential. Some people call it geometric potential. This is the potential you are really interested in. And you see that this potential really depends on lambda. So for different lambdas, these potentials are different. And if you really want to push forward, push down, the measure from the symbolic space, which is the most important measure for every lambda, you would like to push forward the most important measure, then this is going to be the most important measure. Maybe this is multiplied by a constant, but somehow the most important potential is a constant multiple of this. And this potential really depends on lambda. So for different parameters, you really need to push forward different measures. This was the idea of what we did. And with the existing method, it was not possible. And these horrible things, what we have committed over there, this is a 77 pages paper, full of technical lemmas. But the essence of this, that if both the measures depend on the parameter in a smooth way, and the iterated function system depends on the parameter on a smooth way, and the iterated function systems are very smooth, and you know the the interaction between the variable of the function f lambda x, so x and lambda is also smooth in all possible way, everything is smooth, very smooth. Then you are not going to lose dimension when you come down from the symbolic space to the line. You take different parameters and different measures and you project it down. Then for typical parameter you do not lose dimension, and if the entropy of a Lyapunov exponent is bigger than 1, then the projected measure is going to have is going to be an absolute continuous measure V L2 tens. So this is the essence, and I hope that this is understandable, and I'm sorry for being extremely boring for this. It is very ugly technical details, but I do not want to get into more details. So the next time, what I plan to do, on the other one hand, I would like to mention applications of this theorem. It does not require anything, just this summary what I gave. And I also would like to talk about, hopefully I will have time, I would like to talk about something different, but what is related to this theory, and which thing is actually written down in a joint paper. It is partially written down in a joint paper with István Kolozsvári, and this is about one of my favorite topics. Is that if you have such an iterated function system with overlaps, then the coding is how much unique the coding. We will consider a condition which is will be called almost unique coding, which means that almost every point in the symbol, you are in the symbolic space, you go down to the attractor, and you get a point on the attractor. How many codes such a point has? And if typically only one, then it is the almost unique coding. And we consider another condition, which will be the weak almost unique condition, which means that you have the symbolic space, this is the symbolic space, you throw away a set of zero measure from the symbolic space, and then you restrict yourself what you get after throwing away, whether the coding is unique or not. And then there will be another condition. These two things have been written down, and we now are putting it here. But maybe I will also talk about another condition, which is a kind of separation condition, weaker than the open set condition, what I call exponential distance from the enemy condition. That's another thing. That will be more uplifting than this one. Okay. Thank you very much for your attention.
Forward to the examples. Thank you again.
So on the later theorems, was T still a hypothesis? Were you still assuming T, or did T disappear? So this is theorem 2. There was the theorem. Maybe.
T is transversality.
Yeah, in theorem 2. But there's a theorem 3, I think.
Yes.
Possibly a theorem 4. I can't remember.
Yeah, but T is assumed.
May I, for a second?
Yeah.
Just stop the recording.
Good idea.